Good morning, Dr. Majid.
Yeah, just yeah, ma'am.
Yeah, this is Dr. Bal Desai. Saloni is joining.
Yeah, sure. So am I audible?
Yes, you are audible. Yes. We will start in 5 minutes.
Yeah, sure.
Good morning, everyone.
Good morning,
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am. Good morning, everyone. Payal ma'am, shall we wait for a few minutes more or shall we start?
Yeah, I mean, are you expecting few more students to join, or otherwise we can start? No, not an issue.
We can wait for 2 more minutes, I
Yes.
think, then we can start. Yeah. All right, I think we can start now. So, a very good morning to everyone. Good morning, Dr. Majid Hussein, our expert for today's technical seminar. Dr. Payal Desai, Coordinator, Civil Engineering Department, Navrashna University. Dear faculty, friends, and my dear students. I welcome you all to today's technical seminar on liquefaction of soils in Gujarat. It gives me immense pleasure to introduce our expert speaker, Dr. Majid Hussein. Dr. Hussein holds a first-class B.Tech in Civil Engineering from National Institute of Technology, Srinagar, Jammu and Kashmir, India, and a PhD in Civil Engineering with a specialization in Geotechnical Engineering from Indian Institute of Technology, Gandhinagar. After graduating from IIT Gandhinagar, Dr. Hussain has worked as a postdoctoral researcher at MAREI University, Cork, Ireland, on European Union-funded CELKI project to develop an improved design tool for marine energy foundations and mooring system. Dr. Hussain has several publications in international journal, renowned international and national conferences, and several book chapters as well. He is currently working as Assistant Professor in Department of Civil Engineering, National Institute of Technology, Srinagar. On behalf of Civil Engineering Department and School of Engineering and Technology, Navrashna University, I now invite Dr. Majid Hussain to enlighten us with today's seminar.
Thank you, Dr. Saloni, for the kind introduction. Good morning, everyone. So, am I audible?
Yes, Majid, sir, you are audible. Yes, Dr. Majid, you are audible. Please
So,
go ahead.
I am presenting. I think I hope my slides are visible now.
Yes, yes.
Yeah.
It is visible now. Yes.
Yeah. So today we will be discussing actually liquefaction, and particularly we will be focusing on the liquefaction that is observed during the earthquakes, and we will discuss both the global scenario and the Indian scenario, and we will focus on the Gujarat, the 2001 Bhuj earthquake. And we have recently, I think it was on 11th June, a documentary was released for that. You can see it on the YouTube also. So the brief outline of today's presentation or the talk will be like, so we will first discuss what liquefaction is, and then we will go about the incidences of earthquake liquefaction at the global level and the Indian level. After that, we will also discuss about the basic framework for the evaluation of liquefaction, how it is evaluated, what are the parameters that are required for the evaluation, and how do you say or how do you decide from the deterministic analysis whether a given site or whether a given soil element at a given depth is liquefiable or not, and how close it is to failure due to liquefaction. And after that, we will see a couple of videos, and we'll also discuss about the determination of this liquefaction resistance from field tests as well as laboratory tests. So the first thing is that what is liquefaction? Now, if you see, it is a hydraulic condition in which actually what happens is that in a saturated soil deposit. Now, soil, as you know, it is a three-phase media, right? It has soil and soil particles. In voids, there may be water or there may be air or both, right? So when both they are all the three present, then it is a three-phase media. And in liquefaction, we are focusing basically on saturated soils, that is soil plus water. However, recent studies have found that the liquefaction can also occur in dry soils depending on the intensity of the loading. So if it is of impulse type, like you have a ballast or you have a, you can say tunnel explosion, then it can also occur there. However, we'll basically focus here on the saturated soils. Now, if you look here in the first diagram, this is a normal soil here. So we have a saturated soil deposit consisting of granular soil, and the voids are filled with water, right? Now, this bar here shows the total stress that is acting at any depth. So it will depend on the total bulk unit weight of the soil multiplied by the depth, right? Then there is this pressure, water pressure there, that is hydrostatic. So it will also depend on the unit weight of water and depth. So under normal conditions, when there is no loading, soil element is resting there, you can say you have the difference of these two, the total stress that comes, it's the difference of this effective stress, it's the difference of this total stress subtracted by pore pressure. And as you know, the shear strength of the soil, it is actually a function of a effective stress, not total stress. And we are mainly concerned with this, how it behaves, what are the changes that occur in total this effective stress when water is there, when water is not there. So any change in effective stress is reflected as a change in the engineering behavior of the soil. Now this is the normal condition. Now all the load that is carried by the contact between the soil particles, and that is what actually effective stress is, because water has zero shear strength. It cannot resist shear force, and whatever shear resistance has to be there, it has to be from the soil contacts. And you can see here these arrows, they are at the soil contacts. The magnitude of these arrows actually shows the magnitude of the stress, contact stress, that is the effective stress that is there. Now when you load it, now when you load it, what will happen is that the pressure at time is equivalent to zero at the time of the loading, that will be actually carried by the water. And as per the Pascals, that pressure will increase. You can see this pore pressure increasing, right? Now there are two conditions. If you allow this pore pressure to release, that is dissipation of the pore water pressure, then there won't be that much change in effective stress, because if this is permitted, the drainage is permitted, the release of the pressure is there, then it will remain as hydrostatic. However, you might have seen or studied about soils, about their permeability. So any layer that is impermeable, like you might have a clay sand, you might have clay soil deposit surrounding this soil element here, right? Soil element here, then it will be undrained case. Now in that undrained case, if you apply load, the pressure that was increasing, that gets trapped there. Now as it is increasing, the pressure at this point, it will be same. Now let me, I think I should just a second. So I hope my video is visible right now. Yeah, is it visible?
Yes, yes,
Yeah.
we can.
So what happens is that if you see these interlocking of the soil particles is there initially. Now one water pressure is there. What will happen is that this water pressure that is developing and that is actually not allowed to move, that separates these particles, and in between what happens is that the contact force reduces. When the contact force reduces, you can see this effective stress decreasing. Now as this effective stress decreases, the shear strength of the soil decreases. Now in the limiting case, what will happen? The loading is such that very high pore water pressures are developed. The permeability is such that it does not allow the water to drain out. Now what happens is that this pore water pressure almost reaches to the total stress, and what happens to the difference we can see. So it nearly reaches to the zero. And this limiting condition where the effective stress reaches to zero, that is what actually initial liquefaction is. So you have effective stress reaching to zero, and from the shear strength property, you can see that the shear strength in cohesionless soils is a function of effective stress. Now, if this becomes zero, what happens to the shear strength is it will also become zero. Now, once it is there zero, we have some load there. So earlier it was resisted by this effective stress. Now this resistance is here, this. Now load is still there. What will happen is that the building will sink. Now because the soils are not homogeneous, they are heterogeneous, everywhere this pressure will be different, and that will lead to differential settlement. In extreme cases, sinking of the soil, sinking of the low, you can say the overground structure into the soil happens in the limiting condition, and that is what this liquefaction is. Now this liquefaction, what happens generally in this is that soil grains are there, water pressure increases, the contact between the soil particles that reduces, giving a condition of zero shear strength. Now in extreme cases, this may reach to zero, but that is for purely cohesionless soil. However, if you have a cohesive soil, there might be some apparent cohesion and you may still actually have reduction in shear strength, but it may not reach to zero. Now in that case, now suppose you have a load acting 100 and you require actually 150. That means you are at a fixed safety factor of 1.5. Now, for example, even if there is cohesion, your resistance actually reduces to say 90, from 150 to 90, but your load is still 100. That means you are below the limiting failure, and that will actually lead to the sinking. Even if the reduction in shear strength is not complete, then what will happen is that there might be significant reduction in the shear strength in the effective stress that might actually lead to sinking of the overground structures, and that is also termed sometimes as cyclic degradation. Now this liquefaction, this may occur under both cyclic loading as well as static loading, or you can say monotonic loading. Now monotonic loading is in one direction, so you apply load, it applies in the direction, one direction. It can be compression and it can be extension. So there is only, you can say, with respect to time, the sign of the loading does not change. So that is known as static liquefaction. And in cyclic liquefaction, you have a load that is varying with time. So its sign changes. So you can say that there is sometimes it is positive load, sometimes it is negative load. So in that case, it's cyclic liquefaction. Now basically on what factor does it depend? So if you have any material, so be it sand, be it clay, so the factors actually that govern whether the soil will liquefy or whether the soil will degrade in strength, that depends upon the soil properties as well as the loading. So if you have a very loose soil, it will liquefy under, say, even average loading, average earthquake. But if you have a dense sand or you have a highly over consolidated clay, so what will happen is that even under extreme loading of 7.6 magnitude earthquake, it may not liquefy. So it will depend on both the material properties, that is the properties of the soil, as well as the loading. Now you can see here that the static liquefaction, it is mostly observed in loose silty sands, and there are very large number of these actually documented case studies. So the two famous among them are Fort Dam is 1938 and Aberfan, South Wales. So in 1966, around I think 144 people were killed. These scenarios of the static liquefaction, they are particularly, you can say, common in mine tailings. So they actually, what do they do is that the mine tailings, they work in the stone quarries or diamond or gold rigging. So what is happens there is that the fine material, fine rocks, silt type material is there, so they have to deposit it. So once they deposit it, and it is actually deposited by hydraulic jetting. Now in that case, it is deposited at very high water content. Now even when it is staged, so they lay one layer, then above that another layer, you keep on adding the load. And in some cases, the bottom layer that experiences this static liquefaction, leading the static strength becoming zero, nearly to zero, and then leading to disaster. So there are very large number of case studies of mine tailings failing by static liquefaction. Now in cyclic liquefaction, it was happening earlier also, but then people did not realize it. So it was actually in 1964 Niigata earthquake in Japan, where people actually realized the damage caused by this cyclic liquefaction due to the earthquake. So it was, you can say, at that time, Niigata was actually well-developed city. It was a modern city at that time. But when they realized that the structures are actually intact, so they have only failed in terms of function because of the, you can say, differential settlement, tilting. You will see in next slides what were the scenes there. Then there is 1971 San Fernando Dam was also there in California, in Japan. So these are very actually, you can say, common events these days. And 2001 Bhuj in India, which we will focus in coming slides. Then 2011 in Japan, Fukushima was there also. The recent one was also in Christchurch. So 2011 Christchurch in New Zealand. So it actually presented a large data with respect to the liquefaction. So because this Christchurch is based underlying by sandy silt material. So it ejected onto the surface, and you can actually Google it how much amount of silt they have to the municipal corporation of Christchurch have to actually remove. So at some places it was around 1 meter thick silt. Now here you can see that in static liquefaction, right? So if we have this stress path, I hope you are actually familiar with this. Now if you start with this here, this is the general stress path of a, you can say, loose soil, very loose soil. Now if you have dense soil, you can see this resistance, you can say diabatic stress, that is increasing, as well as this confinement pressure is also increasing. However, for a loose soil, when you load it, it always reaches to the stress origin. Now at stress origin, what is your actually this condition? Your P dash effective confinement pressure is 0, your deviatoric stress is 0. That is actually resistance. Now any load, if this soil was sustaining some load here, now because of the static liquefaction, it has reached to this resistance. So it does not have any resistance to bear that load. So ultimately what will happen is that it will actually flow this red path, the soil having this stress path, it will actually flow. That's also known as flow liquefaction, right? Now in dense sand, you can see this P dash is increasing and resistance is increasing. So we do not need to actually worry about the dense soils. Similarly, in cyclic liquefaction, now you can see there was monotonous decrease or increase in the P. However, in cyclic liquefaction, you can see that if you start from here, with the number of cycles, you are actually moving towards the stress origin. And what happens at the stress origin is that your effective confinement, that is reducing, and your shear stress, you can see here this vertical axis, that is also reaching to the 0. That means under both conditions, be it static liquefaction or be it cyclic liquefaction, there is loss of effective confinement, that P dash, the sigma dash which we discussed here, that is there is loss of this effective pressure. And we know that the shear strength or the load bearing capacity of the soil is a function of this effective confinement, and it loses this function when liquefaction happens. You can see this global scenario is, this was the first thing I was talking about, the Niigata earthquake. You can see here these the buildings are structurally intact. There is no structural failure. However, the foundation soils have liquefied, that has led to the actually tilting of these structures, although they are intact, but you cannot go into them because it scares you. So it is the functional failure. Structurally they are intact, the beams are fine, the columns are doing fine. Similar, the slabs are also doing fine, but electricity may be damaged because this tilting may lead tension in the electric wires. The water supply will be damaged. So it is a functional failure. Similarly, you can see the Victoria home at Howard here tilting. Then this, once you have this earthquake, it may lead to liquefaction. And if any transmission tower is on a liquefiable strata, that may cause fire. So these are actually secondary events then, fire, liquefaction after the earthquake. Then you have this Loma Prieta earthquake 1989. Here you can see that this road has been damaged. You can see these longitudinal cracks here. This pavement is also damaged. Then we have this San Fernando Dam here. You can see this is very large landslide happening here. Then Marina district, once again here, this is the sand boils. So this is from the Christchurch. You can see this car that has sunk into the silt that was ejected because of the 2011 earthquake. And the recent one that we had, I think there was one in 2021 also in Indonesia. So we will have one video of this, how scary it looks, 2018 Indonesia. Now let's look at the Indian scenario. So that was global. Now in India, these earthquakes and the liquefaction that has been actually dated back, it dates back to actually 9th century, 1829 to 1971. So there are features that have been actually identified by seismologists. So Seismological Research Institute is in Gandhinagar, Ahmedabad. So they have actually identified these locations. And it was actually coincident that at the same place, within 1 century, they had 3 liquefaction events. So you can say that it is actually pertinent to a specific place also, how the soil deposit is there, will it liquefy or not. So same place liquefied in different earthquakes. So you can see the history of the liquefaction in India. So the most documented is actually 1897 Assam earthquake, which is actually famous for this thing. So they have actually vertical accelerations greater than 1 g. So that's pretty huge. That means greater than 9.8 acceleration in the vertical direction. That means the rocks were ejected out. And if you go through a cursory Google search about the Assam earthquake, you will see that on the hilly slopes there are rock outcrops that are actually attributed to this vertical acceleration. So 9.8 in the vertical acceleration is too much, actually very huge. Then there was 1934 Bihar Nepal earthquake, and you can see here that the cracks, or you can say fissures in the ground were around 15 feet deep, 30 feet wide, and around you can say 900 feet long. So these are typical fissures or ground crackers that were observed in Bihar Nepal earthquake. And once again in Bihar earthquake 1988, because it lies in the foothills of the Himalayas, so it is seismically active. And in 2015 and or I think 14, there was also a huge earthquake in Nepal, that Kathmandu earthquake. Now let's turn to the Bhuj earthquake, that is actually the focus of this presentation. So you can see this seismic zones of India. This is adopted from the recently modified IS 1893 part 2016. These are the seismic zones of India. Now you can see that Himalayas, they are fine. They are in the seismic zone 4 and 5, but there is this one patch here and here. They are in the 4 and 5 zone. So why is it that? So if you look at the earlier version, so before 2001, they were not in this zone. So they had different zones, second and third. So this one is actually, I think, to Lato earthquake, and this one is attributed to the 2001 Bhuj earthquake. So after 2001 Bhuj earthquake, these were modified. These maps were modified. You can see that Bhuj is in 5 zone. That is the highest risk zone in India, and then the surrounding area is in 4th zone, zone 4, and also the neighboring country, that is Pakistan, that has also this damage during that time, that also has similar this seismic risk. Now why after 2001, why not before? Now before, it was in 1956 and I think 1819 in Bhuj. So Allahabad fault is there, so they had similar earthquakes, but the damage was not there because population was less, economic activity was not less. So this 2001 Bhuj event, that has very high impact, disastrous impact on the economy, on the lives of the people. Then it was modified, although the faults in and around Gujarat, they are intraplate. That means within one plate, they are not plate boundaries there. So within one plate, they are active there, and this 2001 Bhuj earth forced the, you can say, the policymakers and the engineers to actually modify these seismic zones of India. These people from Gujarat, or the students from Gujarat, might have came across these images. So these are from the Bhuj 2001 earthquake, and in these 4 images you can see all the damage that is actually attributed to liquefaction. Now in one, it is a Khauda road. You can see this sand boil, the liquefaction has occurred, and now this sand along with the water as a fluidizing material has escaped to the earth. So it will find the path that occurs very low resistance and it comes to the surface, because as you saw that the pore pressure that is increasing, so that will always find its way to this bit. Even after the earthquake, even if it is not actually permitted to escape at the time of earthquake, it will, after the earthquake is gone, maybe in 10 days, maybe in 7 days, it will escape. So it finds its way to the surface, and you can see the sand whiles here. And this watch is, or a compass, is actually for scale reference. So it gives you an idea of how big this is. Similarly, this one is Fatehgarh Dam, that is in Bhuj also. So you can see these cracks. So this is the upstream portion of the Fatehgarh Dam. Here on this side it is a reservoir. Now reservoir means that the soils were saturated. That is the perfect condition for the liquefaction under a given earthquake. Now this crack, you can see that is on the upstream, it is in the longitudinal direction. This was formed because what happened is that as the water level was, actually that was fortunate that water levels were low, they were not filled, otherwise it would have caused flooding in the downstream area. Now what happened is that water saturated sediments were lying on the foundation of this embankment or dam, right? Now they liquefied. The load was there. The load was this embankment here. It is around 6 meters high embankment. It was there. Now when the soil had this very low resistance, so it caused it to flow. So you can say it was a type of a lateral spread. This is not liquefaction. It is an effect of liquefaction. So liquefaction occurred in the foundations of the foundation soil, and that reflected as an effect in the overground structure, that was embankment. Similarly, here you can see slope of this Fatehgarh Dam. So that is, you can say, upstream toe, and this is the service road there. So this was actually, you can see water here. This was subsiding towards the upstream into the reservoir as a result from the liquefaction of the foundation soil, and foundation soils were sandy in nature. Now you can see that sand is there, water saturated sediment is there, and magnitude, very high, 7.6 moment magnitude earthquake strikes, and this creates a perfect condition for liquefaction. Similarly, this one you can have this, see this is a sand boil. So sand boil is a feature of liquefaction which is formed when this fluidized material comes to the ground surface. So this is from run of Kutch, a sand boil. This is for a scale. So you can see that it is around 2 to 3 meters in diameter. Now that was on the embankments of the dams and sand boils. Now let's look within the dams also. So this one, this Chang Dam that was damaged, it suffered most damage there. So you can see that within this reservoir also, the sand boils were formed. So because of this liquefaction, so these sand boils came to the surface. And while I went there, so I had a visit once there. So I talked to people who were actually eyewitness to the earthquake. And according to them, so downstream of this dam, they had these water fissures or water jets coming to around 12 to 15 feet high. So that much pressure you can see. And this is once again the same dam on the upstream toe. Because of the liquefaction, you can see this thing going into the reservoir. So this is a typical lateral spread. So in liquefaction, you have many features that happen. Sand boil is one, lateral spread is one, and this one is Budarmora. So it was, you can say, a residential area there. Water was not there, but this crack here, you can see, even it was dry, the liquefaction of the underneath soil where water was there, that pushed the fluidized material, that is the sand, silt plus water, to the ground. And these cracks, they were actually 3 feet wide. These cracks and around 4 feet in depth. And at the same place, you can have these sand boils. So this is the cap of a lens here. You can see the size of these sand boils there. Let's come to the this 2001 Bhuj earthquake, how if it affected the structures. So actually it created a lot of structural damage, but here I am actually linking only those, you can say, incidences where liquefaction actually magnified the damage. So you can see this pair here, bridge side, this sand was liquefied, and this pair here, actually it lost the firm ground because it was liquefied, the strength was reduced, and air was actually, you can say, deviation of this deck from the spear. Similarly here at Wound, this pier, so underneath this pier there was liquefaction, and that actually led to the tilt of this deck. You can see here this coming. Now these are disasters. You cannot actually then retrofit them because these are very heavy structures, and this damage, it might seem a very small crack to us, but this is a structural damage. It is not a functional damage that it may scare you, but it's structurally fine. But it is a structural damage, and it was actually attributed to the liquefaction of the soil that was actually beneath this pier here. Now, for further information, you can go to the NICE website that is maintained by IIT Kanpur to get an idea. Now let's move to the basic fundamentals we can say here. Now, do all soils liquefy? So we have different soils. You can see here on this plot. So in this axis we have an increasing particle size, and we have percent fine. Now, Chida in 1970 they did an analysis, and it is an observational analysis. That means they identified liquefaction sites, then collect soil samples from them, and then actually did this grain size analysis. Now what they found is that this size is most liquefiable soil. So if given a chance, if you have a magnitude, some moment magnitude earthquake, say 6 or 5, and if the soil is saturated, confining pressure is not that much. Why confining pressure is not that much? We will come to that. These soils, this range of soils is most liquefiable, and these ones, they are potentially liquefiable. That means if this liquefies at 5, this may liquefy at 6. Now you can see this grain size, this corresponds to actually silt and sand, this one, and this one is clay and gravel. You can say coarse sand here. Now what will happen is that, let's come to this thing. Now if earthquake is there, it is saturated, the permeability is very less, right? But it has cohesion, so that cohesion actually prevents the soil, or actually it prevents the effective stress to reduce to 0. So it is there, something is there, so there is reduction, but it does not go to 0. And here if you see this coarse sand, it has good permeability, high permeability, right? And also the size is high, that means the gravitational force, the weight is very high. So it is difficult to actually keep the pressures or hold on to the pressures, because the soil is permeable. Even one drop of water flow will release the pressure. You can do that practical. So one drop of water will reduce the pressure. So on this side it is high permeability, on this side it's cohesion. So that prevents actually effective stress reducing to 0. So what happens there? So it is sand plus silt. Permeability is not that good. Cohesion is not also there. So it presents a perfect picture or a perfect conditions under saturated conditions for an earthquake to liquefy this type of soil. Now you can see this sand and silt, this is most liquefiable soil. So if given a chance, if you have an earthquake and you are sad, or you have to decide which type of the soil will liquefy, so you have to go with the silt plus sand. So sandy silt is most liquefiable soil under given conditions. Now let's look at the cut soil. So this work we have done at IIT Gandhinagar, so it represents actually 32 soils, and if you see the grain size distribution, so this range A between these two, that is actually the range for most liquefiable soil. This is most susceptible to liquefaction, and if you see that for most soils, this part and most of their gradation that comes within that range, and it's because that of this thing that these soils were liquefied, these soils liquefied, and you have many actually scenarios, many incidences of liquefaction during 2001 and also during 1956 Anjar earthquake, right? So it is this whole Kutch region. So it is believed that it was a low-lying area. So it comprises of sand and silt, and you might be surprised that the silt is actually coming from Rajasthan, not from this you can say Arabian Sea, right? So it has a sandy silt, and that fitted between these boundaries for most liquefiable soils, and that actually led to the liquefaction. Now, till now, what we have actually discussed is actually the effective stress principle, that how the soils behave under loading if drainage is not permitted. Then we saw actually what are the incidences of earthquake liquefaction at global level, and then in the Indian scenario, and then we saw actually how the soils liquefy as per their gradation, as per their particle size. Now we will discuss actually the framework of this liquefaction. Now the earthquake comes, soil is there, it is saturated. Now what will happen? Now first thing is that we have to actually calculate, or we have to measure the intensity of the earthquake. Now it is measured by moment magnitude. Now to an engineer who is interested in liquefaction, or to a researcher who is interested in liquefaction, he has to actually extract the information from the earthquake that is relevant to him, that is relevant to liquefaction, and that is termed as cyclic stress threshold, CSR. Now CSR is actually the load that this earthquake puts on the soil element. It is the seismic demand, so it will depend on the site, it will depend on the moment magnitude, it will also depend on the intensity of the earthquake and how far the earthquake the site is from the epicenter. Now cyclic stress ratio, you must remember that it is the load that this earthquake puts on a soil element. And cyclic resistance, it is the capacity. So you have two things. One is you can say demand, another is capacity. Demand you can say it is load, capacity it is strength. Now strength by this capacity, strength, that is capacity strength by demand, or capacity by demand, that is our factor of safety. If your capacity is very high as compared to demand, that means you are fine. There is no need to worry. However, if it reaches close, if the ratio reaches to 1, so in the numerator we have the capacity, that is strength. In denominator we have the load. So that ratio actually gives you, if it is large, that means you are away from the failure, limiting failure. If it is say 1.2, even 1, so below 1.2 you say that liquefaction might happen, right? Now how this CSR is actually calculated? So it is actually the ratio of the average shear stress that this earthquake creates and to the overburden. Now overburden, it is actually dependent on the depth. So you might be at some depth and you will calculate this overburden. So it will be simply depth multiplied by submerged weight, right? And if you create calculate this shear stress, it has been converted to a uniform cycles by Fourier transformation. So you say that 65%, that is 0.65 of the maximum acceleration in the horizontal direction that is recorded in at the ground level, so Amax, and you normalize it with 9.8, that is G, and you have this overburden, total overburden, because load will, whenever you calculate load in any geotechnical problem, it has to will be with the total stress, because water is comes also with the total stress. Now in resistance, we saw that the resistance of the soil is a function of effective stress. So it will be a ratio with respect to effective stress. So this term, that is 0.65, and this thing, so this gives you an average shear stress, this ratio, let's see, so 0.65, and this Amax by G, and this total overburden, so it gives you average shear stress. And if you divide it by this effective overburden, that gives you the ratio. And this RD, actually this factor, it takes into account the flexibility of the soil, because as you go down the below the ground level, the soil is confined in the horizontal directions, right? Now you can see how this RD varies with respect to depth. Now up to 20 meters, why 20 meters, or also we will also discuss this. So you can see with this depth it decreases. So it reaches up to 0.4. So minimum value of 0.4. So less than half, right? So this means that even if you are at say 20-meter depth, if you follow this curve, this load is reduced by 2.5 times than at the ground level. So for similar conditions, same this Amex, you can see here it is 1, it is 0.4. That means a reduction by a factor of 2.5 times, right? So that is why, as I said, this 1 meter in Christchurch, liquefaction is a surface phenomena. So it occurs actually within 2 to 3 meters, and it may also occur even at say 40 meters, but that effect does not reach to this surface then. So even if liquefaction occurs here, so the effects won't reach here. However, if you have a pile going down here, it may create this lateral force on that pile, right? So these are the correlations that you can get from any, like if anyone is interested in further you can see review on this, this is the best thing that is available for liquefaction. So this was a workshop in 1996 and 1998. Then it actually happened over 6 years. Then the results and discussions were compiled, and you might find actually you can see there are number of authors, actually 21 authors are there. There are two papers. One has only two authors, one is Jude and another one, but that was retracted then because there were a lot of authors who had contributions, right? But most of the time that one is cited, and this one is the corrected one. Only the authorist was corrected. You can have detailed review of this paper, and you will actually appreciate how this liquefaction happens, what are the factors that come into picture, and this is a deterministic approach, you can see, right? So in this slide, we mainly focused on what is the load that an earthquake applies on a soil element at a given depth. Now depth is taken care of by this, right? And the moment magnitude or the intensity of the earthquake is taken care by this 65% Amex G and this. So this is the load that is actually related to the magnitude of the earthquake. And this RD, as I said, it takes into account the dynamic response of the soil column. You can see that with respect to that this decrease. Now, as I said in the previous slide, that this earthquake liquefaction is a surface phenomena. That does not mean that it does not occur at deep depth, say 300 or 30 meters. It occurs, but the effect does not reach to the surface. Now you can see here. Now this bold line here, this is the resistance. You can see resistance means that the soil, if load is below this, there will be no liquefaction. However, at any time if the load gets above this line, this dash, this solid line, you will liquefy, the soil will liquefy, right? Now this is the resistance of the soil, or you can say this is the load required to create resistance, right? So it is a property of the soil, and from properties, it depends on the type of the soil, it depends on the relative density of the soil particularly, and the over-consolidation ratio. Now an earthquake comes and that applies this load, that dashed one. Wherever this load gets larger than the resistance, that region, that zone is actually liquefying. So that is how you actually create a profile, a vertical profile section of a site, and decide which depth or which layer of the soil is going to liquefy, because soil is not homogeneous, it is heterogeneous. You have layers, you might have a clay layer, you might have a sand layer, you might have a gravelly layer, and all of them respond to earthquakes differently. And once you calculate this you can say factor of safety, that is CRR by CSR. CSR we saw in the previous slide how we calculate it. CRR we will discuss in coming slides. Now yes, the soil element at 30 meter may liquefy depending on the load, depending on its density, depending on the water saturation. So it will liquefy, but it is very unlikely that the effects will reach to the surface. Similarly, even at 300 meters, a soil can also liquefy. but the effect does not reach to the surface, and it is at the surface that you realize that if sand boil is coming out, that liquefaction has occurred. Now in most cases it is 2 to 3 meter, however in Christchurch it was observed up to 8 meters because of the intensity of the earthquake as well as the soil conditions. Now CSR was done. So how do you actually evaluate this liquefaction potential? So for that you need CRR, that is cyclic resistance ratio. Now generally for a well and good analysis, you actually require it to be computed from the field tests, but there are also laboratory tests. Now among field tests, the most common, you might know, that is SPT. This is the most widely used. Then we have CPT, cone penetration test, and it is also known as seismic cone penetration test. Then we have shear wave velocity also. From laboratory tests, particularly for liquefaction, we have these two, triaxial and cyclic simple shear tests. And these two, they are used to actually evaluate dynamic properties at small strains. And these dynamic properties at small strains, they are actually very useful and required. They are required for the dynamic analysis of the soil. And you might actually appreciate here that this liquefaction is a large strain phenomenon. So any test that you are using to compute the cyclic resistance ratio CRR, that has to actually induce shear strains that are in the large strain scheme. So we will discuss the shear wave velocity does not come to in that picture, but it is affected by the soil properties in a similar way, not proportionally, it is affected by a similar way as is affected by CRR. So it can be said that we can relate CRR with shear wave velocity, but most cases you will see SPT and CPT. Now the CRR actually it is a function of these penetration resistance. So what is SPT? Actually you penetrate or push a sampler into the soil and measure the resistance. Similarly in CPT you push a cone and measure the resistance. Now the CRR is a function of this SPT. Greater the resistance, greater will be the CRR, and it is also a function of magnitude scaling factor. It is also a function of effective overburden, that means depth. So you have to consider the depth at which you are conducting it, this test. It is also a function of initial static shear stress. So now initial static shear stress means that if you have a building or if you have a site that is loaded, that will have a different response, or if you have an open ground. So that is this how it takes into picture. Now let's see with the SPT. So this image I have taken from the same paper that I was discussing, 2001 UR paper. Now you can see that on this axis I have CSR and CRR. So actually they are same thing, but you define them differently. Now CSR is the load that this earthquake applies, and CRR is the resistance that the soil has. Now if I relate them, CRR is actually the load or the CSR that liquefies a soil in say 15 or 20 cycles. I hope you got it. So anyone can you tell me please that what is the difference between CSR and CRR? Nirav Patel. So am I audible?
Yes, you're audible.
Yes, sir.
Yes,
So
you're audible.
could anyone tell me the difference between CRR and CSR?
Sir, can you listen to me?
Yeah, you are audible.
Okay, sir, I'm Mushrat Kazi. I would like to say that cyclic stress resistance is what earthquake, the load given by earthquake, and CRR is the load taken by soil due to that earthquake load.
Yeah, partly you are right. CSR is right that you said that it is the load that the earthquake imposes on the soil column, and CRR is the resistance. Now you can say, like in structural analysis, you have load and resistance, right? So load is the structural load, and you design for resistance. Similarly, in design a section for resistance. Similarly, in soil, the CSR is the load that this earthquake imparts, and CRR is the resistance. But they are same thing. Now, when CRR becomes equivalent to CSR, that is when the soil liquefies, right? Now, when the soil liquefies, it is up to you. How do you decide it? Now, if you are actually doing a conservative design or conservative analysis, that means you want to be safe. That means that you can say, okay, let's take CRR as the CSR that would liquefy the soil in 5 cycles. Now liquefying soil in 5 cycles, that means the resistance has to be very high for it to be safe. Now if I say, let's say that CRR is equivalent to CSR when number of cycles is 15 or 20. That means a given load liquefies the soil in 15 cycles. Just a second. So greater the number of cycles, if you say 20 cycles, that means you are overestimating the resistance, right or wrong? So if I say soil will liquefy in 20 cycles, and if I say soil will liquefy in 5 cycles, which one is conservative? So a soil liquefying in 15
20.
cycles. Okay, 20. Why?
The one which is, sir, I just want to know conservative in the sense which one is preferable or.
No. So I want to have a safety factor of say 1, say 1.5, right? Now if I keep 2, that means more conservative. If I keep 3, that is conservative, right? In that sense. So you want to stay away from the failure. That is what conservatism means. That means you are using more material. So if you have a section and it has a factor of safety 1.5, now you increase its section, right? You increase the reinforcing balls, you increase the concrete. That means factor of safety increases to 2. However, you are being too conservative. You end up using more material. It ends to be very costly.
Okay. So you gave us the two scenario where the liquefaction occurs in 20 cycle and liquefaction occurs in 5
5
cycle.
cycles.
So the liquefaction occurring in 5 cycle will be more conservative as
Yes.
per me.
Yeah, you are right. Think over it, right? I may be wrong, right? So this is the curve. So this is the resistance and the CSR you get. So what you do is that in field, you do an SPT well, you do an SPT test at a site, then you apply some corrections that we will discuss and compute this N160 here. This thing you compute, and then what you do is actually, let's say you have this 20 value. You go this and see where it intersects these curves. So these are observational curves. So these are not any, you can say, analysis or anything. So these curves have been fitted, and if you fit these, and this is the equation of the fit, and these dots here, these are the observations from the field actually. So above this, the soil has liquefied. Below this, the soil has not liquefied. So if you have this count, say 20, and you go up, it meets here, here, and here. Now you have to see what is your fine content. Now let's say you have 20. So it will be in between this and this. So you compute it, you linearly interpolate, right? So you arrive here. So you have this resistance, suppose 0.35. Now any earthquake that imparts a load below this, that will not liquefy it. And any this earthquake that imposes a load that is CSR of 0.35 greater, that will liquefy it. Now you can see that this was in 2001 adopted, but the data is very old, so it is 1985. And recently, you can see there is number of dots here. They have increased. So these days, more data is they have a actually database, a separate wing working on that. They are actually adding databases, observational databases, wherever earthquake is happening. So they go there and see where liquefaction has occurred, and they then compute these coordinates, that is the N160 and CRR and CSR, and then plot the point. And then these curves, they have actually changed a lot since then. So this is the original paper, and you can see they have been modified, right? So you can see that this is the one here. This is same from this paper, and 2004 and 2008, in 3 and 7 years, how much it has changed, right? So it keeps on changing. So this the red ones, they have liquefied, and these no liquefaction. Now you can see here these white ones also. So they are above this but have not liquefied. So there are some exceptional cases also, right? So what are the cases? So it might be that the conditions were not good, like permeability did not let this to liquefy, although it has very high load, although it was loose, because this gives you the denseness or looseness of the soil here, right? So I hope you will be able to compute it. So once again I will repeat this. So you get this plot, you get this from the field test, what is the resistance, that is the SPT resistance of the soil, and you correct it for some corrections that I will discuss. So for example, you computed it to be, say, let's see 30. Okay, here. So it does not intersect anyone. Any curve, that means soil will not liquefy. It won't liquefy. Why? Anyone? Even here, let's say 30. So it liquefies here. So your resistance is 0.5. And if you see these earthquakes, they have these loads of say 0.15, 0.2, 0.3 is maximum. Even this, that means if this is 30, if it intersects here, you have to have a resistance of 0.55. That means CSR greater than 0.55 will liquefy the soil. And it is very unlikely actually to get that CSR from an earthquake. So it won't liquefy. Now let's come back to here. So you can see 30, it is not liquefying. Can anyone tell me that why there are very less data points corresponding to 30? Anyone? So anyone familiar with the overburden correction and dilatancy correction? So what does an SPT value of 30 say about the, you can say, denseness, about the relative density, about the OCR of a soil? Rahul Shah. So any SPT value, if you see dilatancy correction, you apply after 15. After it is corrected for overburden, if it is greater than 15, then you apply dilatancy correction. That means this soil is dense. That is why you apply dilatancy correction, right? So this 30, that means the soil is good. It is very dense. So it will have, you can say, a response like this. You can say dense soil and static liquefaction. So this P is increasing. It won't liquefy. That is why you see very less data points actually greater than this 15. So most of the data points that you see, they are here. Also, you can see. Why? Because if your SPT value is 15, say less than 20, the soil is loose. Above 20, it is dense. So generally it is taken as 30. If it is 30, then dense soil, it won't liquefy. If below that, you have to do the analysis, right? Now let's let's discuss few things about this SPT, how it is done. So what you do is actually you push a hammer, a split spoon sampler here, you hammer it with some weight that is around 63.5 free falling weight. The fall height is actually 750 mm, right? That means 75 centimeters, right? Fall height is that, and this sampler is pushed. Now you can see this is hollow here, right? Now when it is pushed, it collects samples. So it collects a disturbed sample, right, which you use to run analysis like grain size distribution, Atterberg limits, you can use that, right? Now the sampler here, why I am discussing this, because it has something to do with the SPT value. Now you can see there is this diameter here and this one, they are different, right? The inner, this part, it is for a lining. So sometimes you want to line it there, so you add some liner. So if it is hollow, then you have to apply a correction. If it has a liner, then you have a separate correction. Now you have resistance coming from here, this point resistance. So it is a circular section actually. So you have vertical section, point resistance is coming here, secant friction is coming here, right? So you hammer it, right? So this is the rod, you drop this weight, that is 63.5 kgs from a height of 750 mm and count the number of blows. So this you can see this sampler is actually 450 mm, that means 45 centimeter. Now when you push it, so first the number of blows required to push first 15 centimeters that you ignore, then the number of blows required to push second 30, that is 15 to 30, and then 30 to 45 that you add up, that gives you the measured value in the field, SPT value, right? So once you have that SPT value measured in the field, that is an M, suppose it is 30, then you apply some corrections to get that N160 here, N160, and then that you use to compute the CRR. Now this N160, it is based on US recommendations. Now generally you use this as one in India. So these corrections, there are 5 corrections. First one is the overburden correction, because as I said that penetration resistance is a function of the depth at which you are determining it. Then there is energy correction, then there is rod length correction, bore correction, and then sampler correction. Now first one is the overburden correction that you might be familiar with. So this is the typical one that is used, but it has been, the recent studies have showed that this overburden correction not only depends on the depth or the overburden, but it also depends on the relative density, and that relative density has been taken into account by the N160 value of a clean sand. So you have a clean sand, you do the test at different relative densities, and then you see what is the value at, say, 40 relative density, 50 relative density, right? So this one is same, you can say this is actually here for different densities of sand. And you can see, so it starts from 2, at surface it is 2, and at 100 kPa pressure, that means around 5 meters, it is 1 actually. So can anyone tell me why it is 100 here? Why not 200, 300? See, every calculation has some reason. So it is related to actually 100. Why? Because your atmospheric pressure here, PA, you involved. So this curve, this equation will give you this curve. And PA is actually, atmospheric pressure is actually around 98 kPa. So generally you take it 100, right? 1 bar. So 1 bar that you take, that is 100. That is why it is 1. So at 1 atmospheric pressure, this correction is 1. Now below that, if you are say at a depth of say 10 meters and it is saturated, so up to 9, if you are measuring SPT as say 10, then you have to apply, increase it, it will increase. Now let's say where it is here, so 1, 3. So if you are at a depth of say 2 meters, so it will become 13. However, same value, you measured it 10 at this depth, so it will be 5 only, right? So the explanation for this lies in the Mohr Coulomb-Ferrer criteria, right? Why is it increasing? Why is that decreasing? You can play with that plot. That is tau f is equal to sigma tan phi, and then you will get the response hopefully. Then there is this error energy correction. So once you are dropping the hammer, there is friction, right? You may not be releasing it properly. Now we take only 65 60% of the energy whatever is measured. Now in India, what we say is that this ERM is also this 60%. So whatever is theoretical, this is 60%, then 66 becomes 1. So in India, you take it 1. Overburden correction that is done, and you can see that if you take into account this and that you will get here. Then CRR is the rod length correction. So if you have shorter rod lengths, that will have different correction. If you have longer rod lengths, that will have different correction. And the fundamental is the wave propagation of in an elastic material. So in an elastic material, it is not soil. It is rod is made of this cast iron, or it is mild steel MS. So how the wave propagates, because once you drop the hammer here, right? So you drop the hammer on the rod, the wave propagates, stress wave, actually the stress wave, it hits the sampler, and because the soil is infinite media in the vertical direction, the soil, that wave reflects back and reaches the anvil, and that is how this rebound takes place. This hammer, after hitting the anvil, it may or may not rebound. It will depend on the rod length, right? So it is generally related to the velocity of the stress wave in this material, and it has to be, the length has to be actually related to the velocity wave and time by 2L by Vs. So time will be 2L by Vs. So if your rod length is greater than that, that means you have to take these corrections into consideration, right? So greater the rod length, 10 to 100, that is fine. This wave has enough length to travel. However, if it is less, then you take a rebound of this stress wave. And it is because of this that you realize that it is during the first couple of blows, in fact, first blow, that there is largest penetration. After the subsequent blows, the penetration decreases. Then bore diameter correction is also there. So if your bore diameter is different, so standard is it has to be up to 100. Generally it is 100. If it is 100, then it is 1. If you increase the bore diameter, you have to increase this correction. Then sampler correction, as I said, there is this space. So if you have a liner here, then you have to take this correction into consideration, right? So it will also depend. Now, if you are doing this SPT as per recommended procedures, actually this borehole and this sampler correction, they become one. Then you are left with rod length correction, overburden correction is always there. Energy correction in India, it also becomes one, right? So basically this one is the most important one because it changes significantly. You can see after a depth of, say you have unit weight of 30 meters, unit weight of 20 kilonewton per meter cube. So that means 30 will be achieved in 15 meters dry soil. This reaches actually 0.6. So this one significantly affects your SPT values. So that was SPT value. So once you have done calculated this, you go back to this plot and see where your fine content is and measure the CRR. And once you have that CRR, then you go here and measure the CSR. Now you have both CRR as well as CSR. You take the ratio CRR divided by CSR. If it is greater than 1, okay, but it may liquefy. But if it is greater than 1.2, you are safe, right? Similarly in CPT. Now in CPT, you don't require a bore, you don't require a hammer, so you actually push it continuously. So you push a cone continuously into the soil and measure the resistance that it offers. And meanwhile, while you are penetrating it, you also measure any change in pore water pressure. Now pore water pressure is very important in dynamic analysis of soil, particularly in liquefaction analysis. Now if you have both pore pressure and resistance, it is an icing on the cake, right? Because you don't require here borehole, you get continuous data here, so you get more parameters here. Now you same thing on the y-axis, here this changes. So you have this corrected tip resistance. So you measure tip resistance, then correct it. We will discuss that how, right? And this is also from the same paper. Now you can see in 2008 it has been updated, right? Now you can see there are a lot of changes, right? This bold line and this line, they are from the same paper. 2004, that is 3 or 7 years from that workshop, initial workshop. And if you develop the equation of this curve here, so this is the equation that has been developed by Robertson and Reid 1998. So this workshop actually 2001 compiled that data, all the observations, and got here. Now you do an SPT, correct this CPT resistance, calculate it, and then let's say you are here and you see here for clean sand, if you reach here, that means any CSR that is above this value, that will liquefy the soil, and any CSR that is below, that will not liquefy it, right? So this one is the more latest one. So they have released one more version of this in 2014. In SPT, as you did not have this pore water pressure measurement, here you can see you have this pore water pressure measurement. Sleeve friction you can measure here. There it was, but you cannot measure that. So here you can measure sleeve friction, you can measure this tip resistance, you can measure the pore water pressures here, right? Now how you do it, that you push this cone into the soil by you can say hydraulic jacking system, or you can actually directly apply the load of this truck in increments by a reaction mechanism. This is a rig, so you apply this load, it penetrates. Now that resistance that it actually offers to this driving cone, that is measured here, that is the tip resistance. This collar, it has pore pressure sensors, it measures the pore pressure sensors, and these things here, sleeve, so it has sensors here and here, it actually measures the skin friction. So you get basically 3 parameters here: sleeve friction you get, tip resistance you get, pore pressure you get. And this has electric cables that actually record this, so you don't have to actually do manual reading. It goes into the data acquisition system and you get actually plots like this. So at the site you get a plot like this here. This is the tip resistance, this is the sleeve friction you can see varying, then this is the pore water pressures. So these are the major values here. Then this is the sleeve friction ratio. Now this ratio is this sleeve friction ratio, that is sleeve friction divided by cone tip resistance you get here, right? Now this has been observed that the sleeve friction, that it increases with the fine content and the soil plasticity. So a look at here will actually give you an idea about the soil type. That is why this comes. So they have softwares right now that instantly, once you are driving the cone, you get these parameters, these two, tip resistance and sleeve friction, pore pressure, then you calculate this, and from these values you know the type of the soil. And actually it's a rough estimate, and Robertson and Wright in the same paper 1998, they actually developed a soil behavior chart that is actually determines the soil behavior index, IC, that you might actually see in that paper also. Now once you have this, right, so you correct this tip resistance by applying some factors that are given that are not discussed in detail here. Then you go here, you can see here, let's say 50, you have this corrected resistance 50, and you go here, you can see this resistance is less than 0.1. Now any earthquake that imparts a load of greater than 0.1, that will liquefy your soil. If it is less than that, it won't liquefy. Now both of these, that is the SPT as well as the CPT, what they did to the soil, they actually created large strains. They fractured the soil was being fractured. However, in shear wave velocity, you have two sensors, you create a shear wave and record at a receiver. So you have a source, you have a receiver, you create a wave, shear wave, by hammering or by a sledgehammer, and measure the velocity, this time taken by this wave to reach to the receiver, and then determine this velocity. Now once you have velocity, you determine from it actually shear this dynamic properties, that is the shear modulus, and this has been used to actually compute the CRR. Now you must remember here that Vs is a different mechanical phenomena and CRR is different. Now in Vs there is no fracturing of the soil, no large strain, however it is a small strain phenomena. However, CRR is based on liquefaction, and liquefaction, as you know, it is a large strain phenomena because it is at large strains where pore water pressure is developed. At low strains you don't have any pore water pressure, and then you don't have any liquefaction. And that means if you have a shear wave traveling, it won't actually create pore water pressures at very low strains. But it has been observed that CRR and Vs, they are affected by the same parameters, same soil parameters, and the relationship has been then developed. Now, how do you do it? That we'll discuss also that suppose you have this shear wave velocity measure Vs, then you apply an overburden correction. Once again, you can see this PA, that is atmospheric pressure, normalized with the overburden, effective overburden pressure. Then you calculate this CRR as a function of Vs1. There are two parameters, that is A and B. They are curve fitting parameters that you fit here, and then Vs1, this is the upper limit value of the shear wave velocity for a soil, right? Because once you are doing this this shear wave test, so it may be that the underground is a tank, iron tank, but you don't know, right? Shear wave does not know what material it is, but when you have different values, so you come to realize that okay, this value, this is not of a soil, this is of an iron, right? So this has this limiting value here. Now, how do we determine it? There are different tests. Seismic tests like refraction test is there. So you have this source, you have these detectors that actually detect only this reflected soils, rays of light. And here in refraction, these detectors actually detect refracted rays only. Then you calculate how much time they have taken and do the analysis and see what's the velocity and then relate it with the shear modulus. Similarly, in cross-hole tests, you have two boreholes. Here you have a emitter or source. Here you have a receiver. You know how much distance is here, and then you create a wave and see how much time it has taken. Then you get the velocity, and velocity is related to shear modulus like this, right? Now, how you do it? Like here. So this is the distance. You create a wave. It receives. You determine how much time it has taken. You got this Vs value, and then you relate it with Gmax. So that is what you actually determine from shear wave velocity test. So you determine Gmax actually, which is a dynamic property at small strains. However, liquefaction is a large strain phenomena, but from Vs, you can see Vs1 is the corrected one. So you have Vs, you got this. So this is actually related to some other properties like dynamic analysis. Now in downhole, you have only one borehole. Now, once you have only one borehole, you have receivers all through the depth at different depths, and then you create a wave using a sledgehammer here. You strike it with the hammer and then see how much time these waves take to reach this. So it will be different times because lengths are different. Also, this one is intercepting different layers. So you analyze this, then see how much is this time and how much is the velocity, then calculate Vs1. Once you have this Vs1, you go here and see where your soil lies and what is your CRR, then CRR divided by CSR, then you got the factor of safety. Now some videos I hope it will run. So this is in Indonesia, Palu 2018. So you can see these things moving. So the underground soil has actually liquefied, right? You can see this house is moving, right? So it is floating on a, you can say, liquefied soil fluidized sand plus water, it is floating, right? You can see these structures floating, right? So they were on the ground, but because of the liquefaction, the underground soil, it liquefied, and it has, once it has liquefied, then it will move down the slope like water with high viscosity, nothing else, only viscosity will be there, right? So it will flow slowly with large force, right? So one more thing, this is from Christchurch, New Zealand. You can see that the sand that has liquefied, silty sand, that is ejected. So you might read about it because the authorities has released this document about it, that the earthquake did not did that much damage as was by this liquefaction, because the cost to remove this silt, it as was around, you can say on an average 10 centimeters all through the Christchurch. So they have to remove this silt and find safe dumping places for the silt. So it was very costly for them. You can see that the water being ejected out. So this pressure has to be ultimately released. Whatever pore water pressure gets developed during an earthquake, if it is highly permeable soil, it will release during this earthquake as well as after the earthquake. If it is a low permeability soil like clay, SC type soil, clay sand, then what will happen is that it will take time to dissipate, like here. So earthquake has gone, but water is still ejecting, right? So along with the silt, along with the sand, because it depends on the pressure that was there. Higher the pressure, greater or larger size particles will be also ejected along with the final material. So these were the field tests. In lab tests, you have cyclic triaxial, right? So this is a typical image of a cyclic triaxial. This thing goes in the vertical direction. You have this confinement pressure, and then I will tell you what will happen. This is the actually control panel here. So you apply this load to this sample. You can see, I hope it is visible here. This sample is there. You apply load it in the axial direction, but in earthquakes it is actually in the horizontal direction. Now here are two things. Now you can apply in lab load as deformation, that is known as strain control. You can see this shear strain is constant, and you can see the load decreasing. And you can have load control, load constant, shear strain increasing. This is what happens in the generally in the field. So you apply the load, once the soil loses resistance, then it will deform like this. Now here you apply strain, once the pore water pressure gets developed, shear stress reduces. Now once this shear stress reduces, this is the strength that is reducing. You can see this pore water pressure, it is increasing, this thing is reducing. Here you can see strain increasing as well as pore water pressure increasing. So in strain control, what you do is that you apply load as deformations. Let's say you apply 1 mm this amplitude here with a frequency 1. That means in 1 second it will do 1 cycle with maximum amplitude of 1 mm right here. So it will be 2 mm then. So 1 mm is this one above this axis. Now in load, you can say I apply say 10 kilonewton, or let's say 10 kg of load at frequency 1, then deformation will increase. So this is cyclic triaxial test. Another thing is the cyclic simple shear test. So I have included only these two tests which deal with the large deformations. So this is the cyclic simple shear test. This is the specimen here. So specimen size is smaller here, and this actually goes in the horizontal direction. So it simulates the earthquake tension much better as compared to the triaxial. In triaxial, it is in the vertical direction. In cyclic simple shear, it is the horizontal direction. So these are the rings here. So it makes them flexible. So this thing moves to and fro. This thing is at a constant, you can say at a fixed position. Thus it shears the soil. Now here you can see. So this is the triaxial sample. You consolidate it by applying the confining pressure. Then you apply a load that may be strain controlled and load controlled. It goes up and down as a sinusoidal wave. However, in cyclic simple shear, you consolidate the sample here, then you apply the sinusoidal load but in the horizontal direction. So shear strain is the same. Here it is axial strain of 0.4. Now if you multiply by 0.4 by 1.5, it will be 0.6. So it is shear strain, it is axial strain, that is the conversion. Otherwise both are same here. So it moves into the horizontal direction, which better simulates the earthquake condition. Now this is how it looks like after in this lab the specimen has failed or it has liquefied. You can see the wrinkles in the membrane. So what happens is that the pore pressure is created. Once that pore pressure is created, these wrinkles are created into the around the membrane as you can say the visual inference of the liquefaction in the sample. So this is how this cycle simple shear specimen like this. So these are around 20 rings, so they can move flexibly, right? So they can move over one over the another in the horizontal direction, thus simulating the earthquake conditions in a better way. Here are some references you might find useful, particularly this one, that paper I was mentioning. So it has two versions, only there is authorship conflict, otherwise same. And there are some things by this Idris and Bollinger 2008, 2010 and 14, which gives actually a detailed procedure for liquefaction and analysis using particularly SPT and CPT. So if you have any questions or you want to discuss anything, let me know. So I'm up for the questions.
Yes, sir. Mushrat here.
Yeah.
Sir, from your very informative presentation, we got to know that sand boil is a feature of liquefaction.
Yes.
But as per my little knowledge, uh, sand boil also gives result to quicksand condition. So, out of curiosity, a question arises that what is the difference between liquefaction and quicksand condition? Is it interrelated or both different, or quicksand is a subset of liquefaction? I just want a clearance.
Yes. Thank you. So nice question. So what actually quicksand condition is that it may happen without this earthquake also. Like you have a seepage underneath a dam, right? If your critical gradient is nearly 1, right? In that case, what will happen is that the downward force from the weight of the soil that is balanced by the this seepage force. So that will lead to the quicksand condition. In liquefaction, and that if that quicksand condition happens beneath say 1 meter, if that is given a chance to move out, right, so that will also form a sand boil. But in that case, in quicksand condition, the area involved is very less, so it does not have that much energy, that much force to actually go to the surface if it is actually happening underground. Now if this quick condition is happening at the surface, then it does not form sand boil. It actually leads to piping failure, erosion, right? So that is how you design actually then filters, protective filters. However, this sand boil, it is a feature, it is a manifestation of liquefaction happening at some depth. Then this find is this fluidized material, because the load is very high, the pressure is very high, and the area involved is very high. It finds the least resistance and comes to this what's called the ground surface. So not all liquefaction events are related or you can say manifested in the form of sand boils. So there has to be a condition that the fluidized material should find a vent, find a passage to go to the surface.
Okay,
I
thank you,
hope
sir.
that answers the question.
Yes, sir. Sir, if the soil is after knowing that it can be liquefied, what if the sand is not land is not we can't avoid. Sir, 1 minute. One
Yeah.
minute. Sir, if the construction on the land is inevitable, so what if I provide a pile foundation?
See, first thing is that you avoid the liquefiable soil, right? Second thing that if you cannot avoid it, then either you provide shallow foundations or you go with the deep foundation. Nothing in between. Why? Because at shallow foundations, you can actually provide that flexibility. And deep foundation means that even if liquefaction happens, that won't reach to the surface, right? But it, as liquefaction, as I said, it is a surface phenomena, it is a site specific, so you have to do much more analysis than what I said, that is shallow foundation or deep foundation, like piling. Then in piling, if you have a pile, now that is fine, that at depth that liquefaction will happen, that it won't affect. But what about the intermediate depth? That will liquefy. If that will liquefy, that will create lateral force on the soil, on the pile. Because if you see that K naught for a soil is 0.5, around 0.3. Now what about water? It is 1. So it will magnify your actually lateral forces on the pile. So you have to design for that. Now in case of a liquefaction, and this lateral loading of the fluidized material on the pile, it will act as a beam. You can imagine it like a beam with a uniform load equivalent to the K naught. K naught will be 1 of the fluidized material. K naught is 1. You can simply add water pressure at the depth. So it is at 20-meter water pressure, that is around 200 kilonewton per meter square. On a beam, that is your pile, you have a lateral load of 200 kilonewton per meter square. That is very high. So you have to design for that. So better is to that if you have not started construction yet, better is to compact the soil by dynamic compaction, or if the construction is there, it is already there, then you have to use some ground improvement techniques. Particularly, you can provide stone columns and sand drains to actually expedite the pore pressure dissipation.
Okay.
So this is
Yeah.
very
Okay, sir.
subjective actually. This is a very subjective question, so it has to be site specific. Depends on the location, depends on the site response also, seismic site response also. But these are like major things you can consider, like ground improvement, compaction is there, provide shallow foundations or deep foundations, but consider the lateral loading on the pile.
Okay, sir.
Okay, does anyone have any other question?
Hello.
Yes,
Hello.
go on. Yeah,
Yes.
you are audible.
Yeah. Actually, I'm a faculty here in physics department, and my research area is high pressure physics.
Yeah.
So I found your topic very interesting. I have a couple of questions. I may not be using exactly right technical
Yeah,
words.
no issues. Yeah.
Yeah. So first question is, like it looks like the causes for soil liquefaction is earthquake.
Yes.
So, is it possible to create this kind of a situation under hydrostatic pressure?
Yes, that is what the initial question was. So actually, you just need to, let me go here. So for this type of condition, liquefaction is an actually is name now given. So you just need to make this 0, right? Now,
Right.
if I inject water even at high pressure, the particle contact will be lost,
Right.
gone. So it can be
Right.
created even under static loading. So I apply some load, I drop some weights like you do in impact loading. Impact
Huh.
loading is there. I drop a say 10-ton load 2-3 times.
Hmm.
So even actually what I said that you have to do a ground improvement. So ground improvement uses this technique. Actually, it liquefies the soil. When it liquefies the soil, then it dissipates the pore water pressure. Now, when it dissipates the pore water pressure, the water that was here in the voids,
Hmm.
right, that is gone now. These voids are now filled with the soil particles. That means that in a given volume, now we have more number of particles. Now, more number of particles mean more number of contacts. More number
Right.
of contacts means you have good this effective stress. So ground improvement technique actually uses liquefaction to improve the soil. So you
Okay.
liquefy the soil before constructing anything. Yes, it is possible that you can create this condition without earthquake, like by impacting or even by vibrations. Machine foundation vibrations of higher
Okay.
amplitude can also cause this liquefaction.
Okay. Like this impact means it goes into dynamic pressure experiment. But
Yes.
suppose you have a high pressure cell where only hydrostatic pressure can be applied and no access to inject any liquid after the cell is loaded with the sample. So once the liquid is contained into it, you lock the cell. That kind of an environment we can create here in my lab. So I was just thinking whether it is possible to mimic this kind of a situation in a closed high pressure cell.
So what pressure you are talking? Is it MPa?
Yeah, I go up to gigapascals.
Oh, that's actually soil will crash at 4 MPa.
4 MPa. But it
Yeah,
is possible to create even that
yeah,
low
it is.
pressure.
Yeah, it is
Yeah.
possible. You can attain this liquefaction. What you have to
Yes.
do is that simply fill that chamber with the soil and
Hmm.
then inject the pressure, this fluid at the pressure, say whatever you impart. So it will depend on the density of the soil and the confinement.
Okay.
So soil will crash around at 4 MPa. So
Okay.
crashing comes into the picture. Then if these are 10 particles, it will become 20, it will become 30 particles, then whole physics changes.
Okay. Now, the second question is you mentioned about the soil permeability. So, higher the permeability, higher chances of venting out the pore pressure, right?
Yes,
And less chances of liquefaction, correct?
yes.
Yeah. So, are there any incidences where, let's say, the soil wasn't so permeable, but such kind of liquefaction incidences occurred, and instead of the damage, the surface of the ground there has changed its elevation by increasing the volume, and then also one can reduce the pore pressure, right? Either you went out or you increase the volume if that is possible for some soft soils or soft ground.
No, no, actually by increasing the volume, you are actually reducing the number of particles in a ground volume. So what that will happen is that will actually reduce the soil properties, that is
Oh,
the
right,
soil
right,
load bearing capacity, and then
right, right, right. Yeah,
we cannot do that. So that
yeah.
goes against what soil is meant for to bear the
Okay.
load.
So the liquid only has to go out.
Yeah, liquid only has to
Oh,
go out.
okay, okay. Thank you very much.
Yeah, nice questions.
Yes, so are there any questions? Students, faculty members? All right. Dr. Majid Hussain, it was a wonderful presentation. Thank you so much for your time and your efforts. I now call and invite Dr. Payal Desai, Coordinator Civil Engineering, to convey the vote of thanks.
Yeah, thank you, Saloni. Thank you, Dr. Hussain. It was indeed a thought-provoking and informative seminar. It was quite interesting to know about the phenomena of liquefaction, how disastrous its occurrence could be for any civil engineering structures, and liquefaction potential of various soils in Gujarat. On behalf of Civil Engineering Department and School of Engineering and Technology, Navratna University, I express my gratitude to you for accepting our invitation and taking out time from your busy schedule for enlightening our students. I would also like to thank all the faculty members for helping in organizing this talk and to my dear students for their active participation. Thank you once again, Dr. Majid. We look forward to many such informative and technical talks by you in future. Thank you once again. Okay, Saloni.
Thank you, Dr. Payal. Thank you very
Yeah,
much.
thank you
Thanks
very
for
much.
having me.
Thank you, Majid. Thank you, everyone, for making this seminar a very good interactive session. I wish you all a very happy day and a wonderful week ahead. Thank you, everyone.
Thank you.